Welcome to this video lecture on the subject of multiple regression and non-linear regression. We're going to begin with multiple regression. We already have considered regression models where there's a single predictor variable, x. But suppose we have more than one available predictor variable. Surely we could use two predictor variables or more than two in order to predict y. In this example, we're looking at a regression model that can predict the VO2 max, which is the peak oxygen uptake, an important measure of an athlete's endurance. It might be possible to predict the VO2 max of athletes using both the age and the weight of the athletes. The data that this is based on are taken from athletes who play hurling in County Dublin. The regression equation is quite familiar in its format. Instead of a plus bx, it's a plus b1 times x1 plus b2 times x2. So we have an equation here, which is a linear equation. That is, there are no squared terms or cross terms. And a linear equation in 3 dimensions like this represents a plane rather than a line. So it's not so simple to represent it visually on a graph. The coefficient of age is 0.371, which means that for every 1 year older an athlete is, if they're the same weight, then their VO2 max increases by 0.371. Notice that the interpretation of a coefficient in a multiple regression equation is sympathetic to the presence of other variables in the model. The same is true of the p-values. The p-value for age in this model is 0.001, meaning that age is a useful predictor of VO2 max, even if weight is known. And actually the same is true of weight in this case. The p-value of weight is also less than 5%, telling us that weight is a useful predictor of VO2 max, even if age is known. If we compare these results to a simple regression equation where we predict VO2 max just using age alone, we notice that the p-value and the coefficient are different in value. And of course, this is as we expect, because if you ask a different question, you will get a different answer. So in this simple regression equation, we're just asking the question with the p-value, is age a useful predictor of VO2 max? And the coefficient is addressing the question, what change do we expect in VO2 max if the athlete is 1 year older? We're not on this occasion making any comment about whether the athlete we're talking about has the same weight. We now have a situation where we can use more than one variable as a predictor. And there may be many variables available. In addition to age and weight, we may also have values of the athlete's height, their body mass index, their body fat, and lots of other performance measurements. So the question now arises, what's the best subset of predictors to use? Should we use one predictor or should we use two? And if so, which two? Or should we use 3, and if so, which 3? And so on. In this dataset, there are 12 available predictors, meaning that there are hundreds or thousands of different regression models that could be available. It would be good if we could go through all of those potentially useful models and select the one which has the highest R-squared adjusted value. This would possibly be the best model. We can use software output to trawl through the best subsets and find out what is the R-squared adjusted for all the different models that are on offer. The software output using Minitab looks like this. In the top right-hand corner, we have the names of the 12 different predictor variables. Their names are written vertically if you read from top to bottom. Over on the left side, we have a heading vars, meaning variables. So for one variable, for two variables, for three variables, the software points out what seems to be the best model available. So for one variable, we notice there's an R-squared adjusted of 17.6 available. And going right over to the 12 predictors, we notice that an X is inserted under the variable age, meaning that if we're going to use one variable, then the best one variable is age. It will provide us with an R-squared adjusted value of 17.6. We can improve this by using two variables. That takes the R-squared adjusted up to 24.9, and the two variables are age and weight, which we have already considered. Continuing up to 3 variables, we can improve the R-squared adjusted again, 4 variables, 5 variables. Then it may surprise you that if we add a 6th variable, or if we use 6 variables, the R-squared adjusted actually falls. And there is no better R-squared adjusted for a higher number of predictors. This is not surprising when you think about it. Some information is not useful. It's only contributing noise to the model. And so the model is not improved by adding more and more variables. Those variables may have nothing to add in terms of new information. It's worth noting that the R-squared value always improves, but that's just a feature of the sample. That's not necessarily telling us that the predictors are useful for making a prediction for the population. So R-squared will always improve as more variables are added, simply because degrees of freedom are being lost. But R-squared adjusted adjusts for the loss of degrees of freedom and gives us an indication of whether the new variable is really useful for predicting the response. So this is a very useful piece of output for helping us to select a model. And we need to be careful with this. R-squared adjusted is a good guide. S will also be small. S, the standard deviation, will be small for a good model. And Mallow's CP will have a value close to P plus 1, where P is the number of predictors in the model. So if we just consider some of the caution we need to apply when selecting variables for a multiple regression model, so selecting the predictors. Firstly, as we've said, use R-squared adjusted and not simple R-squared. R-squared is deceptive in that it always seems to improve with the addition of new variables, even if the new variables are not useful. So R-squared adjusted is better to use. Secondly, if moving up from a 2-variable model to a 3-variable model only brings a very modest improvement, it's worth considering whether maybe the smaller model might be better. This principle is called Occam's razor, after William of Ockham, the English philosopher. It's also called the law of parsimony, which means let's be stingy, let's be mean with our model. Let's not be over generous with the number of variables we include, because if there's only a very modest improvement by introducing an extra variable, it could be that that variable is not even significant if we test its p-value. The third thing to take into account is that we want to avoid multicollinearity. This is the situation that arises if 2 of the predictor variables are correlated with each other. And if that happens, it will inflate the errors in the coefficient estimates. A good rule of thumb is if the correlation coefficient between 2 predictor variables is higher than 0.9, then don't use both of them in the model. Use one but not both. That corresponds to a variance inflation factor. An R of 0.9 gives an R-squared of very close to 0.8, which means the variance inflation factor is 5. So 5 is an acceptable threshold for a variance inflation factor. Anything above that is not acceptable. This means that the variance of the coefficient estimate for this predictor is more than 5 times greater as a result of its correlation with other predictors. So this should be avoided. Fourth point to make here is that whenever you select a large number of predictors, there's a possibility that you will overfit the model. That is, you will just end up including variables that are predicting random variation in the sample rather than the underlying relationship in the population. So a low value for R-squared predicted indicates that there's overfitting has probably occurred. R-squared predicted is obtained by omitting the observations one at a time and then using the remaining observations to predict the missing observation. So R-squared predicted gives a good idea of how good the model is at predicting new values of the response. Fifthly, the Mallow's CP value should be close to P plus 1, where P is the number of predictors. And Mallow's CP statistic suggests a good balance between a biased model, which has too few predictors, and an imprecise model with too many predictors. If you already have historic data from some process, this best subsets analysis is a very simple way to trawl through the data for clues about which variables are useful for predicting some important response. For example, the yield in a manufacturing process. trawl through all of the process settings for historical batches and see what is the recipe which gives rise to a high yield. Having said all of this, the most important thing is still to identify all of the potentially relevant variables before you begin. For example, we started there into an analysis of exploring the relationship between VO2 max for athletes with 12 different variables. But one variable we didn't include was the position that the athlete plays in the team. That variable could be worth more than all the others. So before beginning a regression analysis, take time to ask yourself if all of the potentially relevant variables have been captured, because that's worth more than all of the analysis that you will do thereafter. If the information about that variable is not available to you, well, then you simply won't find out how useful it might be as a predictor. We now move on to the topic of nonlinear regression. Sometimes when we draw a scatter plot, we notice that the points have a relationship, x and y, but it's not a linear relationship. This often happens with a dose-response relationship. In fact, it's often called a dose-response curve. And here's the reason why. As the dose increases, the response increases, but the same increase in dose brings about a lesser increase in the response as the dose continues to increase. So there we have a relationship which is not quite linear. We can see there is some curvature. The curve is concave downwards. Now we could go ahead and naively fit a linear equation to the data, and it's not a bad fit within the range of the sample data, but it will of course be a very bad fit as we extrapolate beyond the sample data. If you look in the bottom left corner of the graph, you see the 2 points that represent a dose of 2 units and the rather small responses. Notice that those 2 points are well below the line, and they also differ from each other. So we have here 2 types of error. The 2 points are not at the same height, which is pure error, but also the average of the 2 points is not on the line or close to the line, which is lack of fit. So the software itself is able to identify when we fit a model which is inappropriate for a data set. Pure error tells us how different the points are from each other, and lack of fit tells us how different the points are from the fitted values. And when we construct a model and perform the analysis, we can get a lack of fit p-value. And if that value is significant, if it's below 5%, it's a warning that the model we have chosen is not a good fit to the data, that there seems to be some structure in the errors, which is not simply random, but that there is evidence of lack of fit there. So what shall we do about a nonlinear relationship? The first thing we can do with a nonlinear relationship is fit a nonlinear equation. And the simplest way to do that is a quadratic equation. So rather than just y equals a plus bx, we have y equals a plus bx plus cx squared. And that's a very simple way to deal with the problem. So we add a quadratic term, and this introduces one elbow into the equation, into the curve. And so we see there we have a curve to fit curved data. If you look at the top right of the graph, you'll see these 2 data points that correspond to a dose of 12. If we could move those 2 points horizontally, not to the right, but to the left, if we could push those points to the left, then we could perhaps make the points line up in a straight line. So in a sense, if we could shrink the x-axis rather than stretch it, if we could shrink it, then perhaps we could make these points linear. And that suggests the second technique that we will use. So shrinking the x-axis can be done by applying a mathematical transformation, which would straighten out the curve. Currently, we have dose on the x-axis, but we could use a transformation of dose, like the log of the dose, which will shrink the axis, or the root of the dose. So we can shrink the axis using something like log or square root or 1 over x, or we could stretch it if we needed to stretch it using something like x squared or x cubed. If we take the log of the dose, shrinking the x-axis, you notice that it linearizes this. So this is our second technique for improving the fit for curved data. If we transform one axis, then we have a linear equation of the old familiar type using this transformed variable. You can read more about this in the textbook in Chapter 6.